In today's video, we're going to be talking about something which is called interpolation. An interpolation is the mathematical process of filling in the gaps between data, between points, or between states. If you're in a scientific or engineering context, for example, you might have a table of data reflecting measurements that you've collected for your object. For example, measurements of its density at various points, its temperature at various points, etc. So you have a table of data, a table of measurements, which I might represent visually just by a succession of dots. You may want to predict what is happening between the measurements that you have taken. And so interpolation would give us a way to fill in the gaps between the measurements that we have taken to figure out what might be going on with all of these intermediate points between my measurements. In a context like animation, in particular digital animation, you might be working on animating a character. And so you might pose your character in various ways at key moments throughout your animation. Interpolation would give you a way to predict how the character would move between those key poses. Interpolation is the process of filling in gaps between data or filling in the gaps between states. This lesson is very close to my heart because interpolation is something that I actually use almost every single day outside of the classroom in my personal work and in my hobbies. Because interpolation is used in video editing, interpolation is used in digital animation, interpolation is used when making digital music, and it's also used when doing game design. And that's because interpolation gives you the ability to define what your object should be doing, what your song should be doing, what your video should be doing at a couple of key moments. And then you can just mathematically fill in the blanks of what's happening between those key moments. So I'm going to have to rely pretty heavily on Editor Sam here to show you some examples. Editor Sam, could you please give the people the example of the character that you just animated in Blender? This character was animated by defining the poses at 9 key moments. I created 9 what are called keyframes, 9 poses at 9 key moments. And then the animation between those key moments was created mathematically, just interpolating between those poses. If you could please go out to BandLab, you can also show the people how keyframing and interpolation is used when making digital music. For example, set an instrument at a low volume at one point in the song, and then set that instrument's volume to something higher at another moment in the song. Editor Sam, if you could please show how interpolation is used in video editing to create, for example, a gradual zoom effect. You can keyframe in your video when it's fully zoomed out, And then at a later moment in time, you can keyframe the video when it's fully zoomed in. And then interpolation allows you to gradually transition from that zoomed out state to that zoomed in state. And Sam, if you could also go ahead and show the people what this looks like in a game design context.
Hey folks, Editor Sam here. So what's happening is I'm in the Godot game engine and I'm going to create a method to make this icon bigger. So here's a variable to track how much time has passed. Here is a two-dimensional vector storing the object's initial scale in the x and y direction. And here's a final scale also stored as a two-dimensional vector. So now the code you're seeing me write is a function to let time pass, to let time advance. And as time advances, I'm going to steadily increase the scale from what it was initially to what it should be at the final time. The final time here being when 1 second has passed. And when you run that method and when you run that code, you see the Godot icon getting bigger within 1 second.
In general, interpolation is the tool that you want to use if you want to transition anything from one state to another. There are lots of different ways in theory that you can fill in the gap between 2 points or between 2 states. If I give us 2 different points, I could fill in the gap between them with something that looks a little bit like a sine curve. Or I could fill in the gap between them with something that looks almost logistic. Or I could fill in the gap between them in arguably the simplest possible way, and I could fill in the gap between them using a line segment. And if you fill in the gap between the points with a line segment, that action is called linear interpolation. Linear interpolation fills in the gap between 2 points with a straight line segment. Linear interpolation is used often enough that it gets its own special acronym. This is known as LERP, LERP for short. LERP for linear interpolation. LERP for short. Now, considering how useful LERP actually is, the formula for LERP is incredibly simple and pretty intuitive if you view the formula the right way. If you want to parameterize the line segment between 2 points, or if you want to create a function that transitions you between 2 states, you can use the formula R of t is equal to the number 1 minus t scaling a vector r sub 0 and the number t scaling the vector r sub 1. And in this formula, r sub 0 is a vector representing your initial state or first point, and r sub 1 is a vector representing your final state or your second point. Now, as we use this function is only intended to be used for t values within a certain domain. And the domain of t values is t going from 0 to 1 whenever you use this formula. And we'll talk a little bit about why as we go through the next example. So, quick, simple example. If I want to parameterize a line segment between these two data points, a data point here at 0, 1, 2, and a data point here at 3, minus 5, 4, to predict what is happening between these points of data. Then I can do that by setting up the following vector valued function to generate every single location on the line segment between these 2 points. R of t is equal to the scalar 1 minus t multiplied by the vector representing our initial point, our first state. Here, the initial point being the point 0, 1, 2. So I'll take that point and turn it into a vector 0, 1, 2. Then I'm going to take the number t and use it to scale the vector 3, minus 5, 4. This vector representing our final point or final state. This vector valued function, as t goes from 0 to 1, is going to generate all the locations on this line segment between these 2 points. To demonstrate that, let's go ahead and plug in, for example, the initial time t equals 0. If I plug t equals 0 into this formula, then 1 minus t becomes 1 minus 0, and t becomes 0. So what I have in this expression is basically 100% of the first point, 0% of the second point, and so at the initial time 0, at the initial value of t, we're getting that first point returned to us. So here we are at the initial state. We could plug in, for example, the final time, t equals 1, to this formula. If I plug in that final time of t equals 1 to this expression, then 1 minus 1 becomes 0. So this expression is basically giving me 0% of the first point and 100% of the second point. So as it should, if I simplify this expression, then I'm going to get just the second point back, the final state, 3 minus 5, 4. If I plug in intermediate points, what I'm going to get is, in some sense, a mixture of these 2 points, or viewed another way, a weighted average of these 2 points. For example, if I plug in a t value like 0.25 to this expression, plug in 0.25 for t here and 0.25 for t here, then that produces a mixture and average a combination of these 2 points. If I simplify 1 minus 0.25, what I get in that coefficient is 0.75. So basically what I'm getting here is 75% of the first point or state and 25% of the final point or state. And likewise, as you plug in other intermediate values of t, you're getting other combinations and other weighted averages of these 2 points and states. If you plug in 0.5, you're getting 50% of the first point and 50% of the second point. If you plug in t equals zero point 0.6, then you're getting 40% of the first point and 60% of the second point, and so on. So you can think about this formula as a combination or a weighted average of the 2 states. Let's go ahead and find a function that can be used to linearly transition between 2 colors. I've got one color here, which I'm representing as a 3-dimensional vector by breaking the color down into its red, green, and blue values. I'm imagining a color whose red value is 0, whose green value is 255, and whose blue value is 120. I'm imagining another color whose red value is 200, whose green value is 180, and whose blue value is 20. So let's find a function that will transition me from this initial color to this final color within a 1 second period of time. Because I'm transitioning from one state to another, I can use that LERP formula to create that transition and set up a function r of t equals 1 minus t times a vector representing the initial color, which I'll turn into the vector with the red value, the green value, and the blue value serving as the x and y and z components. Then the value t scaling the second color turned into a vector 200, 180, and 20. And I'm going to run this function for t values from 0 initially to a final time of 1 second. And then over the span of 1 second, this function will transition from this initial color to this final color. Editor Sam, could you please go ahead and code up this method and show the people what it looks like in, for example, a game engine?
Editor Sam here. Okay, so what's happening is I am setting up a variable to track how much time has passed, setting it to an initial value of 0. I'm also typing in a vector representing our initial color, and I'm typing in a vector representing our final color. Now I'm setting up a function that will allow time to advance, and if the time passed is less than 1 second, I'm going to go ahead and create the LERP between my initial and final colors using this function 1 minus the amount of time that's passed times the initial color vector plus the time that has passed times the final color vector. And then I have a method below that is going to take that vector and convert it into a color, and then I'm just going to apply that to a panel within the game. And if we run that code, we can see the transition from that bright green to that orange.
Now, as you just saw, that transition happened quite quickly, right? A transition over the course of a single second happens very quickly. So the question is, how can I modify this function if I want the transition to occur over a longer period of time? Maybe I want to stretch out the transition so that instead of happening over the course of 1 second, it happens over the course of 5 seconds. So I'll repeat what I just said because what I just said has a hint about how we're going to answer this question. What I want to do is stretch the function over time so it happens in 5 seconds. To stretch a function over time, we're going to use one of the transformations that we learned how to do in pre-calculus. If I want to stretch a function so that it happens over a 5 second period of time instead of over a 1 second period of time, what I can do is I can steal the function and I can make a modification. Wherever t used to appear, I can replace that t with the quantity t divided by 5. T divided by 5 here and t divided by 5 here. By dividing the input by 5, we stretch the function over time by a factor of 5, and we cause this function to elapse over the time interval t from 0 to 5. Editor Sam, please go ahead and code up this modified transition function so that folks can see the colors change over the span of 5 seconds. Let's use this idea again to lerp an object from an initial position to a final position. I have an object located at a position 300, 200, and I want to transition it to the position 600, 400 within the span of 10 seconds. Again, I can use the basic lerp formula. 1 minus t, but not just t. I'll do t divided by 10 to stretch out the transition so that it occurs over a length of 10 seconds. And then I'm going to take my initial position and write down the vector that represents it, the vector 300, 200. Then I'm going to take the t over 10, and I'm going to use that to scale the second vector, the vector representing my final position, 600, 400. And this is going to cause the transition to occur over a span of 10 seconds, t starting at 0 and going up to 10. Sam, please go ahead and code up this method to move the Godot icon from this initial position to this final position in two-dimensional space so that the people can see this function in action. Now let's talk about how to create non-linear interpolations between functions. How to connect the dots, how to connect the points with something other than a straight line, and why and when we might want to do something like this. The method that we have just created, the linear method for interpolating between points, can be visualized via this little video. We have our initial state and we have our final state, and we're transitioning between those two states at a constant rate. However, I may want to transition between the states at a different speed. I might want my transition to evolve slowly in the beginning and then more quickly as time progresses. This, for example, could be used if you're trying to animate a falling object. An object falls slowly in the beginning, and then it falls more quickly as time goes along because the falling object is accelerating under the influence of gravity. So how can I modify that linear interpolation formula if I wanted to create an effect of acceleration? If you want to create other types of transitions between your initial and your final point, you can again achieve that by replacing the t in the linear interpolation formula with other functions. For example, if I replace the t by a quadratic function, t squared, then this has the effect of causing the object to accelerate over time. This creates the effect of a transition that happens slowly at the start and then quickly at the end. So you would see something like this, r of t equals 1 minus t squared times your initial state plus t squared times your final state for t's in the interval from 0 to 1. This is called quadratic interpolation. Editor Sam, please go ahead and code up this method to drop an object in the Godot game engine. Now, maybe you want to create a transition that happens quickly at the start and slowly at the end. So maybe you want to represent an object braking or decelerating over time. You can do that by replacing t with a different function. For example, it's common to use a function like sine of pi over 2 times t. Sam, if you could please go ahead and code up this method so that folks can see the transition happen quickly at the start and slowly at the end. There are several different common modifications to the LERP formula that are used to create different types of transition effects. So for example, here is the full guide to the different types of transitions and the different types of easing that you can access within Godot using some of its built-in methods. Linear transition, sinusoidal transition. The third row are functions that use a t to the fifth power, then t to the fourth power, then t to the second power. Here are transitions that use an exponential e to the t. Here are transitions that use a cubic function t cubed, and the functions for elastic transitions and bounce transitions are a little bit more complicated. For example, the bounce transition is a piecewise quadratic, taking the place of t there. All right, that concludes this video on linear interpolation and other types of interpolations. Interpolation can be understood as the action of filling in the gaps between data, between points, or between states. So, for example, in a physics or engineering context, you might have a table of data representing measurements that you have taken, and you might want to deduce what is happening between those measurements. In this case, you can fill in the gaps between those data points using interpolation. In other contexts like animation, programming, game design, etc., you can use interpolation to transition between states. You, as the programmer, you, as the musician, you, as the animator, can go in and define a handful of key states, key poses, or key frames. And then you can use mathematics to figure out what's happening between those key moments. If you want to transition between states in the simplest possible way, transition between them linearly and connect the dots with a straight line segment, you can use the function r of t equals 1 minus t times r sub 0 plus t times r sub 1. Here, r sub 0 is a vector representing your initial state, or the first point, and r sub 1 is a vector representing your final state or your second point. And this transition will elapse over a period of time t starting from 0 and finishing at time 1. If you want your transition to occur over a different period of time, for example, if you want it to occur for t's in the interval 0 to 5, you can accomplish that using a transformation and replace the t with t over 5. If you want the interpolation to evolve in a nonlinear fashion, for example, if you want to connect the dots with something curved like a sine function or a quadratic function, you can do that by replacing the t in the LERP formula with that other function. For example, replace t with t squared or replace t with a sine function. And this is going to cause the transition to evolve differently over time. For example, you can create an effect where the transition happens slowly at the start and then accelerates, or you can create an effect where the transition happens quickly at the start and then decelerates and begins to slow down. All of that can be accomplished by modifying the basic LERP formula in various ways.